right, welcome back for some more advanced physics experiments from PASCO. This session is going to be an explanation and a demonstration of the speed of light apparatus. It's one of our classic experiments and one of my favorites. We are going to experimentally determine the speed of light. And let me explain to you the components that come with the kit when you buy it. So in the kit, you've got this optics bench here, which is what we're going to use to make all our alignments of all the optics. It has a graduated scale on the side of it there. There's a metric scale glued to the side of it there. And I will start from that end. So that is the mini laser. And we use this laser because it has a little L bracket that we use to magnetically connect to this laser bench. And so there's a laser bench aside from the optics bench. And that bracket lets us adjust the height of the laser. So we've had lasers in the past that you can just kind of stick on there, but you can't adjust the height of them. You can adjust the tilt angle, but moving it up and down can be difficult.
So it's a Heaney. Could you use this?
Yeah, so in theory, right?
This is just easier.
Yeah, the experiment is real mechanical. It's real straightforward. And so any laser, in theory, could be used, right?
How did Foucault do it then?
Not with a laser.
He'd even be more famous.
Yeah. So the laser, the height of the laser is important because we want to sort of align the beam in this plane, this optical path here that goes through the setup. And so adjusting that is important. In fact, aligning this thing is probably the most complicated part of this whole experiment. The actual theory behind it and the data collection is not really that complicated. And so the next piece here is a component holder, and we've got a lens on there, right? And so it's a convex lens. That one has a 48 millimeter focal length, and then there's another component holder right here, except this one has a lens with a 252 millimeter focal length. But in between those two lenses is this microscope housing, and there's two parts of the microscope housing. There is the microscope part with a micrometer that'll adjust it. It'll move it back and forth like this. But there's also a beam splitter down there. And so the beam splitter, you can't see it. It's difficult for you to see, but in this housing, directly behind this knob here, there is a partially silvered mirror.
Yeah, students can easily see it here. We just don't want to move it, right?
Yeah. And so just even me touching it, yeah. I pre-aligned this, and just me touching it may have put it out of alignment a little bit, but we're going to go through the alignment because that's oftentimes, like I said, the most difficult part.
And you can, if you have your own optics, you can use those, right? You can buy this separately from the optics, or you get the complete kit.
That's right, yeah. And one of the most important parts of this setup, well, actually, I'll get to that in a second. So the beam splitter, so we're going to send the beam down this bench through both of these lenses, and it's going to get split in half. Or excuse me, I shouldn't say that. It's going to go through this beam splitter here, and it's going to continue down through the second lens there, and it's going to hit this component, which is probably the most important part of this system. It's the high-speed rotating mirror, right? And so there's a mirror in here in this housing, and this housing actually comes with a shroud that sits on top of it like this, and you can thumb screw it down. And the reason it comes with a housing is it spins so fast, it is really loud. It can get really loud. Well, it's not that loud, but it can be loud. And so this helps knock some of that noise down if you're in a classroom with, several groups working on the same project. But there's a motor here. Ooh, did you see that? Just me pushing on it, move the alignment. So there's a motor here, and that motor is connected to a motor controller, which is right here. Right, and that motor controller controls how fast that mirror rotates, basically.
Two speeds, right?
Yeah, and so it's got
plus minus.
Yeah, it's got two speeds. So the previous version of this setup had a like a potentiometer control, right, where you can adjust it through a set of different angular frequencies, or excuse me, angular speeds. This one is configured to, you push the button and it ramps up to one maximum, right, angular speed, and then ramps down and changes direction to some other maximum angular speed, which is what we need to do for the experiment. So it's sort of convenient for us.
Then it go to 750 and then double that.
That's exactly right.
Because when it's going really fast, it can heat up the motor, and that's when you want to collect data.
That's right, yeah.
Fast.
Yeah, so we want to spin this thing as fast as we can. And I'll explain the details of that in just a second. But from this rotating mirror, that beam comes down this bench, hits that rotating mirror, and goes down far field down there. And I don't know, you guys can't see it, but there's a fixed mirror, they call it, way down there, right? So this would be like down the hallway or on the other side of the classroom, right? And you can put it at different distances. And so this fixed mirror is going to catch the beam down there and then send it back, right? So
it's like a focal length of something like 15 feet or something.
15 meters, yeah.
15 meters.
Yeah, so it's something like that. It's like, it was either 13 and a half or
so you want to
15.
be roughly, that would be the optimal distance to have it, but that's not something you can always do.
Yeah, and that's because as the beam comes through the optics, it's starting to diverge. This lens will do some collimating, right? But naturally it's sort of diverging as it goes down there. And so having the curvature to that fixed mirror, right, it's not perfectly flat, does a good job of sending the beam back here at about the same diameter, right, as it left. And so, and the reason we need that is because the beam goes down, hits that rotating mirror, goes down to the fixed mirror, comes back, hits this mirror again, and then comes back down our optics. And that's now the beam splitter plays a role, right? Now some of the beam gets reflected up through this microscope housing, and we can basically measure the position of the beam, right?
It's going to shift.
Yeah, and so, like I said, the actual experiment, the theory behind it's real simple, right? You've got light that comes down, it hits this mirror, and it goes down to that fixed mirror, and if this mirror is rotating fast enough, right, by the time that light reflects off that fixed mirror and comes back, this will have turned a little bit. And so the optical path here has changed. And so the faster it's spinning, the more the path has changed, the more it's sort of diverged, and that's what we're going to use that microscope housing for.
That's the thing that's really, or the PASCO engineering has really done, is you get such a fast rotation, you get a large shift, you get an accurate measurement.
Yeah, and we said 1,500, right? It's not
per second.
That's not revolutions per minute. That's revolutions per second. And so there's a lot of precise engineering that's gone into this housing. In fact, the mirror itself is a piece of metal, right? A flattened piece of metal that has been polished, highly polished to be reflective, because that way there's no like pieces in there that can come loose. Because at 1,500 revolutions per second, things are really moving.
That's like a millisecond pulsar.
Yeah. Okay, and so that's basically it for the components. I talked about the motor control. Oh, the last couple of things I want to talk about, there are a set of polarizers that come with it. So part of the alignment is looking into this housing to see if we can see the spot, right? And if we shoot a laser straight down this system and it's reflecting straight back up in there, right into our eye, we're going to be in trouble.
Bad, yeah.
So we don't want students to do that or us to do that. So we'll use some polarizers here to sort of quench the beam before it goes down there, make it nice and dim so we can see it. And then the final components are a couple of alignment jigs. And so these are intended to be put right on the bench, right? And you butt them up against, there's a little bit of a wall here on our optics bench. And so you can put them in two places and the beam should go right through them. Oops, got it backwards. And that sort of demonstrates the alignment, right? It helps you align the beam down the length of the bench.
But we already did that.
Yeah, but also my secret is I rarely use these because I find that although they're a good sort of starting place, once you've got the optics in place, it's better to sort of just adjust things by hand.
You move the lenses.
Yeah, exactly right. And so those alignment jigs, I'll sort of set them aside over here. And so alignment. So the way that I align this, right, initially is we want the beam coming straight down, hitting this fixed mirror, or excuse me, rotating mirror, and then send it down to that fixed mirror. So what I do is I make sure the beam comes down through all the optics, right down the centers, right? And so you can adjust that up or down or tilt it. So there's a foot under here that you can adjust. So it's going right through the center of that lens, about the center of that beam splitter. That's a little difficult because it's kind of tilted. You know, it's a 45-degree angle right now. But make sure it's set to a 45-degree angle when you're doing your alignment, because if you don't, right, it changes the path of the beam as it goes through there, the glass in that beam splitter. And so if you align it with it not at 45 and then you turn it to 45 for your experiment, it's going to move.
But that dial, as long as you have it all the way down, it's 45.
That's exactly right.
Pretty foolproof on that.
And so straight through this lens, and then we want to strike this mirror, this rotating mirror, right in the middle, right in the center. And so what I do is I turn it around backward. So this rotating mirror assembly has a little hole here behind that rotating mirror that I can put my finger in, and there's a flywheel, right? And that flywheel, I can adjust it with my finger. The one thing that I want to make sure I do first is there's a plastic thumb screw back here. It's used to lock the flywheel for, you know, transit, packaging, that sort of stuff. Make sure that that is unscrewed. If you have that tightened down and you turn that motor on,
then you're screwed.
It's a bad, it's a bad situation. So make sure that this thumb screw is loosened, right? And now I can freely, with my finger, move this rotating mirror. I can rotate it, and you can see the beam sort of going around here, right? And now what I want to do is I want to send it down the downfield, right, to that fixed mirror. And so I just rotate it until and you guys can't see this, but I'm sending it down there sort of near the mirror, right? And now what I'm going to do is I'm going to go down there and I'm going to put the mirror where the beam is, and then make sure it comes right back to where it left from. And so this is sort of a two-person thing. Dan's going to help me. I'm going to go down and adjust it, and he's going to watch to see where the return beam is coming to. And there's actually a horizontal and vertical line on the front of this to help you align it. But we basically want it to come right back to where it was leaving. So I'm going to go down. Oh, and I should say that fixed mirror down there is sitting on a tripod. It's a camera tripod. It's not required that you use a camera tripod, but boy, it makes alignment way easier, because rather than trying to get the beam to hit the mirror, I can send the beam down there and then move the mirror to the beam. And so I'm going to go do that.
Now, I wanted to do this, but we're having a step contest here at PASCO, and JJ's a little low for the week. So he wanted to get a few more steps in, so I decided I would let him do this part. Oh, I see it.
You see it?
It's a little low and to the left.
Okay, so.
And that's you went a little. That's pretty good height-wise. Still a little to the left. And now you're centered. Bring it down a little. Just a little bit, tiny bit. And it might have moved a little right as you did that.
Okay, so let's.
You probably want to look at it.
Yeah.
Then you can get more steps in.
Yes, I'm getting my steps in. So I can, you know, it's the right beam if you block it. Oh yeah, that's real close, right? And so it's hard to tell that there's two there, which is good because we want them to sort of overlap each other, right? But if I block that reflected beam, you see it kind of flashing there. And so very small tweaks can be done using that mirror. There's a XY alignment on the back of it, right? Which is what I was using. But I've also found that if I just move this lens, this L2 lens, if I just wiggle it around on its stand, I can fine tune it to be
right here.
Yeah, right here. Yeah. So what's important is as the optics go down, or excuse me, as the beam goes down through the optics, those convex lenses, they cause it to sort of the beam to sort of go up and down. It's not perfectly flat, right? I mean, that would be ideal, but we could be here for hours. So the beam goes down, hits the rotating mirror, goes down to the fixed mirror, comes back, and it lands right where it was. So in theory, that beam is traveling back through here and then up through the microscope housing, right? Okay, so I've got this little camera here, should be working, I think. And so if I take the eyepiece out, so this housing has the ability to remove the eyepiece like this, right? If I take the eyepiece out, and let me see if I can move my, actually I'm gonna put this on there first.
So our exclusive PASCO screen there.
Yeah. And so let me adjust the exposure so we can see it.
So it is just tissue paper.
Yeah, so what I've got there is just a piece of tissue paper. Right? And so like what I did was I took 2-ply toilet paper and I peeled it, and one of those plies is perfect for this, right? But you can see there's a bright spot right in the middle, right? And so that bright spot is that beam coming back, and that's what we want. In fact, what we want to do is try to get that bright spot right in the center of this opening here, right? And so,
Pretty close.
yeah, it's pretty close. So, but I'll just adjust the beam splitter just a tiny bit, and adjust the micrometer just a tiny bit. And so that should be good. And so what we can do is we can put this eyepiece back in there, and now I'm going to put the polarizers on there, because if we looked in there right now, that full laser beam would, well, it's not full, but the bright laser beam would go.
It's not a good idea.
It's not a good idea.
It's not
Yeah.
that bad.
And
the
so
magnification of that eyepiece
is 9, I think it's 9, is it 90?
That's what I remember.
Yeah, 90, right? And so let me change my webcam to be a little bit brighter. There we go.
So
And
this
so-
webcam part is optional, right? But
Yeah.
I think it'd be a good thing to add to
Oh, yeah.
your lab setup.
Yeah, so I mean, students in the classroom, when they do this, they're looking down the eyepiece with their eye,
Yeah.
right? So I'm up in the front of the class and I want to sort of demonstrate this. This is the perfect way to do it. The one thing that I want to do is make sure the reticle, so there's a cross pattern in the reticle in that eyepiece. I want to make sure that one of those lines is aligned with the bench here. So I'm just going to peek in there and just turn it just a little bit. And so let me see if I can slide that back on there so we can see it. Oh, thought about it. But now you can see some of the follies associated with,
You can see that.
yeah, using, oh, of course I had to touch it. One more. There we go. So, let me just focus a little bit. There we go.
And you get some interference fringes and things
Yeah.
from some of the internal reflections and
Yeah, and we've got those polarizers on there, so the beam is really, it's dim compared to what it would look like normally. In fact, there's some background light that we can't see because the polarizer's knocking it out. But that's the bright spot that we're looking for, right? That's the bright spot that came back through. And you can focus that bright spot, right? So if you adjust the position of this mirror, right, it changes how that beam gets collimated. Yeah, just slight tweaks.
lens?
What did I say?
Mirror.
I meant the lens, yeah. So that if you adjust that lens, and also, well, here, let me show you what it sort of looks like when the mirror is rotating. So we know the alignment's good. We're ready to start our experiment. I'm going to start this mirror rotating, and then I'm going to cover it up. Well, I'll leave it open. It's okay. It might be noisy, but so we'll start it, and you can't see it anymore. That's because you got the polarizers there. If you just pop those polarizers off of there. Yep. Yeah, and so now you can see there's the spot, right?
It shifted.
Yeah, it's moved a little bit, and it should have moved a little bit, right? Because that mirror is rotating now, right? And so there's a couple of things in this image that I want to point out here. Let me shrink that so we can see it better. First is that background red, right? So we've got lots of reflections off of surfaces happening. And so we get this sort of exposure behind that bright spot. And then there's that bright line on the left there. And so that bright line is from the beam, the point at which this mirror is rotating, where the beam comes straight down and then goes straight back through the optics before it makes its way to the mirror down there. And so it's sweeping across the optics before it goes down to the mirror.
So you couldn't see the spot if that was on the spot.
Exactly. And so we can move the spot around by making small tweaks to our optics here. If we just twist the lens a little bit, it moves everything around, changes the focus. Right?
So if you line it up too well, you have a problem, is what you're saying.
Yeah, that's right. If it's perfect, you might have to redo it. So, but this is exactly what we're looking for. And what students are going to do is they're going to align that bright spot right in the center of that reticle, so right where it crosses. I mean, they don't have to. Basically, this spot is going to traverse up and down in the screen here.
Yeah.
And so we need to measure the distance that it traverses, right? And so we do that by measuring the initial position and the final position on that micrometer when it was rotating clockwise versus rotating counterclockwise. And so I'll make some tweak. Oh, and you know that's the right spot. It should go away if you block the beam in between the two mirrors. So if you go right here, see how it disappears? Yeah. But that bright line doesn't disappear. That's how you know you got the right spot. And also, in part of our setup, when we had the tissue over there, to make sure that's the right spot, you want to do that same practice. And then you'll see it sort of flicker. That means you're doing good. You're ready to go. So I'm just going to adjust the micrometer and the beam splitter. The beam splitter is a little harder to adjust. But I'm going to try to get it right near the center of that reticle, basically. And so now we're ready to sort of make our first measurement, right? And so on this motor controller, there are two buttons. One of them starts it, stops it, and makes it go max revolution. And then one of them changes the direction from clockwise to counterclockwise. And so the first measurement we're going to make is when this thing is rotating clockwise at full speed. Yep. And so here
You wait until the very end for that, because that's what can overheat the motor.
Yeah. And so I'll put that housing on just to keep it a little quieter, because it's going to get loud. And so I'll hold this button down, and then it starts to speed up, and you see the spot move. So as the mirror starts rotating faster, the position of that spot changes, right? Because when that beam returns, light goes off of the rotating mirror down to the fixed, and by the time it comes back, that mirror has turned just ever so slightly. And so we adjust the micrometer to put it back in the center, right? And then we record that value, and it looks like it's about 12.69. So about 12.69. So if I go in here, and I say 12.69, I've got the value already in there, right? Now we'll hit the direction button. You see the spot moving? So the rotating mirror is slowing down, and then it stops temporarily and it'll disappear. And now it starts spinning the opposite direction, counterclockwise.
The band disappeared too.
That's right, and the band disappeared. And now, once this thing gets up to 1500 revolutions per second, we're going to track that reticle back to the beam position, that spot position. And so we'll just adjust this to put it back up there, just like that. And this is our second measurement. So we'll read the micrometer, and it's 13.33. That's
by
millimeters.
Reversing it, it's kind of like getting double the speed out of it.
Right.
So it's like you just had one direction at 3,000.
Yeah. And so I'm going to hit stop because we're done. We're done making measurements. And you'll see the beam sort of disappear, right? And then it should, boom, go away because we're no longer aligned with that mirror. And you'll see here, I punched in my values, right? So my micrometer values, it's in millimeters, right? So one was 12.69 millimeters, right? And the other one was 13.33 millimeters, right? And so this equation that's in this file has A coefficient value or constant value, D constant value, and a B constant value, right? And those correspond to physical distances between the optics.
Focal lengths and focal length minus the
Yes,
distance.
exactly. So it's the distance between those two mirrors minus the focal length of that one. Yep. And so I pre-measured all those, right? And
the
punched it in.
manual explains that really well, so students could definitely understand what they're doing.
And the math, the physics isn't terribly complicated, right? Because like I said, it's really a mechanical system. And so the algebra can be extensive and the geometry can be complex, right? But once they've sort of laid it all out there and the manual does this for you, students can derive this relationship all on their own if they wanted to. And so I used this equation here, right, which is in the manual, and then I pre-measured the A, B, and D values, punched them into my calculator here, and then I just punched in the 2 micrometer measurements I made, and I'm
That's pretty good.
My experimental value is 3.015 times 10 to the 8 meters per second.
Better than Foucault.
Yeah, so it's an amazing apparatus for accurately measuring the speed of light, and it requires some setup and some alignment that can be needs to be fine tuned. But once it's set up, we could run this experiment again. If I turn it back on, right there's the spot. It comes back, and we're ready to go again.
So you know why Foucault developed this system? What was he trying to do? Was it just measure the speed of light?
Well, what do you mean?
Well, he had an ulterior motive. This is the mid 1800s, and there were a lot of experiments showing light was a wave, but people still, Newton was still held in very high regard. He is today, but his theory of light said light was a particle.
Oh,
right?
the corpuscle,
and
right?
to explain refraction for particles, it'd have to speed up going through glass or water.
That's right.
And waves would have to slow down. So he wanted to show the speed of light was slower in water.
That's right.
So if you were to have part of the laser path go through water, you could show that. So he wasn't really interested in the value so much, but that it was slower.
Yeah.
And he was the first to show that, and it was a pretty big deal.
Yeah, and there was a succession of sort of ideas and experiments to measure the speed of light.
Yeah.
And this was the culmination that, proved to be really extremely accurate.
And then earlier this morning, we did photoelectric effect, which shifted things back to
Wait, it can
particle.
Be it can be
Although
a particle.
I was reading, apparently photoelectric effect can be explained just by quantizing the energy levels in the metal.
Oh.
And you can use classical field theory. But at the time, they were using it as evidence for photons.
So that is this system. Does anybody have any? Were there any questions?
No questions, JJ.
No questions. Well, thank you very much, everybody, for joining us for the speed of light.
What's next?
Yeah, we have some more great stuff to talk about. We're going to talk about microwave optics, and then we're going to talk about diffraction in just a minute. So,
Stay tuned.
Stay tuned.